Okay, long time ago, when I returned from France, I was alone in Brazil as probabilist. And then I asked Pedro Fernandes, who was my teacher, what to do. And he told me, well, Eulalia is coming back from Berkeley, so you should go meet her at the airport because she's very bright. Well, I didn't go to the airport, but I did invite her. She stayed with us for 6 months, I guess. And it was the beginning of a group of interacting particle systems. I'm very happy to have Eulalia back here. We met again for political reasons, but Eulalia is one of the few persons I know, mathematicians, who is able to attack any kind of a problem without saying, no, this is not my domain, this is not for Eulalia. She's able to, if she's interested in it, she can attack problems, for instance, in neuroscience. And that's, well, I hope she become interested in all the questions we told her. In the last 3 days, we have submitting her to lots of information, questions and questions. So I hope this is a return of Eulalia to this group, and that she returned several times with small intervals of time in between, maybe in 2 weeks again.
Thank you. So thank you, Antonio, for a very kind introduction, and also thanks to Aline and the organizers for this invitation to the seminar and invitation to come here. So what I'm going to talk is joint work with Luis Renato Fontes, Domingos Marchetti, and Tom Mountford. I mean, there are 2 papers, one by the 4 of us, and the other 3 authors. So everybody knows probably here about the Harris contact process. So, but let me say, because it's very simple to describe, let us think that we are the contact process on ZD. So imagine that each vertex of ZD is an individual, which can be in 2 states, 0 or 1. 0 you interpret as healthy, and affected. So an individual which is infected can heal at a constant rate, independent of anything else, rate 1. And it goes from 0 to 1, depending on the number of, let us say we are talking about nearest neighbor, the number of neighbors which are infected. And this and lambda is the parameter of your model. Okay. So it's, okay, well, this is a very classical problem. It was a model. It was introduced by Harris in 1974. What we want to consider is variation of this problem. Our motivation had to do with understanding some things about long-range percolation in 1 dimension. It happens that what we thought could be true, and this could be this model that I'm going to describe could be a very simple thing to see before doing the other thing. What we wanted is not possible. The answer is not what we thought, but this model turned out to be what we initially thought a modelito that we were called. Among us, it turns out to be interesting by itself. So in order to describe it, let me think of the classical, the usual Harris construction of the contact process, which is, it's an infinite system, so you need to do some work. Of course, it is very classical to say that this process is well defined, this Markov process. So use semi-group theory, but you can, as Harris did in a little bit later, you can do the very simple graphical construction, which is the following. So you put here ZD and you put here time. I remember in the old times we always used to draw going down. Then until Enrico Presutti gets, but you always put the time going to the negative. But okay, the time.
You changed it.
Yeah. Okay, so you have on each pair of sides, you have independent Poisson process with a rate lambda in both directions. So these are just arrows that like that or like that. I mean, each one has rate lambda and they are all independent. So n x plus 1, because I'm drawing, let me think, xy, though I'm going afterwards to xy, x minus y equal to 1. This IID, Poisson, rate lambda. Okay, and so these are the times when someone, if here there is someone infected, it can transmit the infection to the other guy, which is there. If the guy is already infected, nothing happens, but that's okay. And the other thing is that the guy can get cured with rate 1. So you put crosses with rate 1 independent. So this, let me call them dx. Okay, they are just rate 1 Poisson process. So this is, and then you are going to say that you want to say this process can be thought as a sort of continuous time percolation. So if you start someone here infected, then, well, it stays infected. Here it transmits infection, transmits, and so on. Here this guy got cured. So in order to know what you have at time t, now you just have to consider CA time t are x. So I put the t there. So dx in ZD, such that there exists a path, and I'm going to say what it means, path from, let me call y, from x0 to yt for some x in A. A is the initial configuration, those guys which were infected. So, of course, since it's configuration here, I am identified with the subset of infected, which means those which are 1. So this is the classical. What means to have a path means to be able to connect following the arrows without crossing any of these marks. This is a kind of a death mark. Okay? So this is the classical contact process. So what we want to consider is a situation where the arrows are just the same, but the times in between crosses are not anymore exponential, because here they are just IID exponential is rate 1. They are, these are renewal processes, so they are just independent random variables with any distribution. So this is the difference of for the process which we consider. So we just replace these guys, no, by dx are the sums of t xi, I going from 1 up to n bigger or equal than 1, where these guys IID and x also, IID with some distribution mu. Mu is, so the parameter lambda is replaced by a distribution mu. Before it was the exponential. So, okay, so This now it's you do the same definition. It's just the same, you know. Just that the only difference is that the crosses are put it. So here is, let us say this is 0. So this is T01. Then this is T. This let me call S202. No, the sums, partial sums. So let me call this guy S and X, X and N, the partial sums of IID random values. So weights. So of course it's not anymore a Markov process because your times have memory, but the interpretation as a percolation system is just the same. I mean, you have this system and you look what you have at time t, and the first question that you might ask, do you see a change, a phase transition as lambda varies? So the phase transition, I mean, that you talk is the same as in percolation, usual percolation, or that means that the process survives forever. If you start with one infected individual, then there is a positive probability that there is an infinite path. So that's the same question, okay? So I'm going to say, to define this, the inf of the lambda such that probability starting from a single guy so okay, that's the same in ZD, just that's the normal definition. So it just says that there is a positive probability of surviving. When you go to more general graphs, then there are two different possibilities. The process might survive, but go far away and don't come back. But in ZD these two are the same. Okay, so let us, for the moment, let us just focus on this definition. So you might say that it's not, it's an acceptable process, even if you think of infection. But it's like there are moments when the guy goes to the doctor and gets instantaneously cured. Okay, but that's there are other interpretations that you might give. The question of mathematical question is just the same. Okay, so I'm going. So I have this notation, which dx for me refers to x space and time. And sometimes I want to speak only about the renewal process, so I use the letter Rx. Just means that I just keep track of this without paying attention about the x. But you don't know that much. So you ask, I mean, what we were asking ourselves, is it possible that lambda critical is 0? Is it possible that no matter how small is lambda, your process can survive, say, in the d equal 1, that's because if it survives in one dimension, it survives in any dimension. So there is a d depending on d, but let us say first I can, not for all results, I need d equal 1. But say, to say if lambda critical is 0 or not, that's the first question. And we were motivated by that because exactly we were considering with Domingos and Luis Renato one-dimensional long-range percolation, and we wanted to put ourselves at the critical, I mean, somehow critical situation and try to give a small epsilon in another component, which will be a small lambda here, and then try to see what we could say. That was our motivation. Okay, but things move sometimes different than what is your initial motivation. So what we can do about these are 3 theorems that I will try to tell you briefly about. I don't know if I will be able to tell you briefly about all of them, but I hope. Anyway, so here D is NED, and I don't want to bother you too much with all the assumptions, so I write in a little bit informal way. If you want, I will do more. So let me put alpha here for T large. and I'm saying alpha is less than 1, and I'm saying plus regularities. So given not to waste, to spend too much time, I just write like that, the assumptions, okay? But then you tell me, this implies lambda critical equal to 0.
Mu is the law of the inter.
Yeah, mu ID with distribution mu. Mu. That before was exponential. Okay, so if it has a fat tail, then plus some regularity, then it goes to 0. Okay, in order not to mess you too much with the assumptions, the exact assumptions, but they are important because, but you can focus on a simpler case that the proof for which the proof is much simpler than what we had to do, which is if you think that mu is in the domain of attraction of a stable of index alpha. So that's a simpler case. So an example that works is L of t, where L is a slowly varying function, like a logarithm. Slowly vary. No, too much. Slowly vary. Varying function. Okay, so I am sort of getting too many g's here, function. Okay, so like a logarithm. So this is an example for which it works, but the theorem works, I mean, you could be oscillating between 2 powers, less than 1, the tails, and still function. So the conditions of our theorem are much more general, but I don't focus too much in order to be able to tell about the other theorem, which I think it's very interesting too. Oops, I didn't. So theorem 2, so this is in the first paper. Theorem 2 is 2 and 3 are in the second paper. So this is an easy theorem, here NED. Suppose that has a second moment, then this implies lambda critical is positive. So this is very simple. This is a very simple theorem, very robust proof. And the reason why it's simple, about this theorem I just mentioned now, and then I don't come back because it's don't need to come back too much because of the time. And why it's in this case simpler, because if you fix any time t here, and you look what's the length of the gap between 2 renewals, since here mu has a second moment, that variable has a first moment. That's a classical simple thing that we teach in the undergraduate courses on probability. Renewal process that has this waiting time paradox. So you need a second moment to guarantee that that one has a first moment. Why? If this variable here has a first moment, is the interval, it's easy for you to think that lambda critical has to be finite, because it's you can imagine very easily that I can compare. So I have here like I think of a branching process. I start, say, suppose these were my 0, I start here, and I see the arrows going down, like the children. Maybe 2 arrows come in the same interval, then I don't consider one of them. I have only one kid out of 2 or more arrows, but I can easily imagine that I can compare this with a sort of branching process. And then I can see if lambda is very small, this rate which I'm going to have will be 2d lambda, and the number of 2d lambda, and the number of guys has to do instead of thinking of number, I think of this length of this interval between two arrows. No, that, and then this if this number is less than 1, you should die after some time. So this is a simple, very robust thing in any dimension. Okay, the third theorem is more interesting. In a second, so the main theorems are this one, which this one is in the paper, and this one in the paper. There are two M's, Marchetti and Mountford. So this is Mountford, this is Marchetti, Mountford. So here we look, so there is a gap, so here is 2 and here is less than 1. So you want to close the gap with alpha bigger than 1. So this theorem, what we would like would be to say, can we prove that if it has a moment larger than 1, then still will have the same behavior, that lambda critical is positive. That for lambda arbitrary small, it's lambda very small, it's not able to survive forever. And well, we cannot do that without extra assumptions. Here the assumptions are regularity. They are kind of simple. Here no, it's a strong assumption. And a strong assumption that I'm going to say. And we can do also, we use path crossing properties, so our proof is only one dimensional. And I believe it's not too hard to pass to higher dimension, but it's very to pass to higher dimension, but using sprinkling techniques, but it's not so clear. Or to say finite range, that might be easy. But it's not so simple, and maybe the effort is not worse. But the worst thing is the assumption we have on mu. So the theorem is if d equal to 1, integral infinite, let me say for some alpha, plus a strong assumption, which is I'm going to assume that mu has a density with decreasing failure rate. Mu has density f with f of t, mu t plus infinity, that's the failure rate, not the probability to die at t given that survived up to t, decreasing in t. So that's so this is a strong assumption. And the reason why that's, I hope to tell a little bit about this theorem. Sorry, I shouldn't have, this is definition. So I put a dot here, just a definition, is decreasing in t. And the reason is because of this one, when we go to this process, we lose many of the properties, of course, of the contact process. We keep additivity because this is just union of set of those guys that can be reached with paths, no? But one important property that we lose is FKG, this attractiveness. And with this property, we have some sort of FKG property that allows us to somehow explore arguments which are of the type Husserl-Seymour-Welch formula of crossing, path crossing in the boxes. And that's why we need. Okay, so let me see. My God, I am too slow. So maybe I will tell very briefly about the first and a little bit about the second, because I thought I would have much more time. I am very slow. Sorry. Anyway, so let me So let me say a little bit about the first theorem. I will not say about all the technical parts, which are the hard parts. Here, the proof in this general situation is kind of involves some trick arguments of coupling. But if you think of those in the domain of attraction of a stable, things the same idea for the construction is possible, and the proof then is not technically, it's simple. Technically simple once you have the same idea. But I don't want to enter into details. So, and for theorem 1, the main technical proposition, say the main technical proposition, I may call technical, but technical proposition is the following. Some property about the gaps. Not the gap. What I call a gap is something in between two dead marks. And so let me say, I'm going to state it, and the proof of this involves several lemmas and several, but I'm going just to say there exists an epsilon, and that I'm going to call epsilon 4 just because I wrote here in my notes epsilon 4, because maybe I will write an epsilon somewhere else, so that, because I planned to tell you about other propositions before, which had an epsilon 1, an epsilon 2, and an epsilon 3. But since I'm not telling, so that for n large and for all intervals, so you are looking an interval very far from the origin, S and T, with, they are very far, so 2 to the n is less than S, less than T, less or equal than 2 to the n epsilon 4. So it's very far away. The interval is after 2 to the n, and the length is less than 2 to the n some power. One has the probability R. R is the renewal process, so let me call R the set, here, Rx. But since there is no x, it's just about a renewal process, I don't need to write the x. So this is Rx, the renewals. The set of renewals, where I have the crosses. Okay, such that the probability that R intersects this interval, the probability that you find a cross in this interval, is less than 2 to the minus n epsilon 4. Okay, so the interval, you have a t very large, the interval has a length at most t to the epsilon, and the probability that there is no, let's say the probability that you have a cross mark there is bounded by t to the minus epsilon, the same. Okay, once you have this, it's easy. So the marks. Easy to imagine what you want to do. We want to say that the process survives forever. It's positive probability. In fact, since we just showed that survives forever, we in fact just will need only instead of z, n, and we will consider only errors in one direction. It's enough, since we just want to say this lambda critical, which is the weak survival. Okay? So, the idea is simple. You want to say, well, you want to say that the probability that it's like a Pyr's argument that you want to use, essentially. You want to say that survives, so you want to say that you pay, or some sort of Borel-Cantelli, to say that you pay a lot in order to kill the process. Okay? So, I'm going to, so I think here is my graph, which is just n. So this space is here, so 0 here, and here is I. And as you see, I'm going just to use errors in one direction. So the idea is very simple. Your process starts finding longer and longer gaps, which it tunnels through, and it finds a very long gap, so it has a lot of chances to go in the other direction, then finds another, still longer one, and still longer one, and still longer one, and then it survives forever. So it's simple, okay? And there is something which I didn't, some lemma which I should have stated, because I killed all the lemmas, but there is one that I couldn't have killed, which is this one. The probability that R intersection T KT is empty, no empty, is less than, let me state exactly as I had stated here, in order not to mess. Some k, any k. So this uses doesn't use all the technical assumptions, but since I didn't want to bother you, the probability that this guy is empty, inf on t bigger or equal than something, than 1, is positive. Oops, I put it stay bothering. So the probability that you have a gap from t to kt, k is any k, perturbed k. K is fixed, but you are going to use a k, say 4, doesn't matter. There is a k that we are going to use. Okay, so if you are at any position of time, and you ask what's the probability that finding a gap between t and 4t, then this is bounded, find a gap like this bounded from below. So after a while, there is a constant c, so you find after a geometric number of searches, you find 1. Okay? So let me imagine that I have the first event here, call it A0, I don't know why the 0. Say T01 is bigger than something. Okay. 4 times T0, does it go? I think so. So T0 is going, no, it's, some number which I'm going to choose later on. Okay, so I have saying that if I start with the guy here at time 0, it leaves a lot. I mean, this T0 is to be chosen. Then I look L0, L1, so on. So L0 is going to be 0, this space. So this is L0. So I look Li is the first time after Li minus 1 that I find a gap which is very big and well located for me to pass through. So this is going to be the inf of k bigger than Li minus 1 such that dk, d is the dash mark, intersect k cross t0 2 to the I T0 2 to the I times 4, so I write like that, is empty. Okay, so I have here L1. So in L1, I will have a gap. So this guy was from 0 to 4, and I start 0 times 2. So I have an overlap with this one. This is 4 times 0. I start here, and my gap is goes up to T0, 8. So it grows, okay? 8 T0. So now I will start, the next time I will start here, I will start a gap from here to by another 2, and go like that. I am multiplying by 2 and so on. So I'm finding these guys, L0, L1, L2, and so on. And that's obvious from what we just wrote here in the lemma, that these ones are geometric, because you are keeping the same rate, the same 4. Because this is some t, this is t times 4. Okay? Because there is a positive probability of, say, let us call this a c, positive. So it's going to be 1 minus c times something. Okay? So, and moreover, if I know everything up to here, what comes here is independent. I condition on the sigma field with all LIs and all the deaths up to here. Everything, I don't know anything in front here because of the way things are. So due to that, you can put the following bad events for which you can compute the probability and see that the thing will survive. So I want to block. Now I started with one guy here, so it survives up to here. So if I find the errors to go from here up to there, inside this region, I am here, and I have bigger. And then I keep going. And I want to say that the probability of this happen forever is positive. So I want to say the probability that I block this is less than 1. So I want to block. So things, I want to say things which, 3 bad things that can happen, and if they don't happen, all of them, then I survive. Okay? So this is Li bigger than Li minus 1 plus I log of T0. Now I need to increase, otherwise I don't get the probability getting very, very small. So the probability of this happen is going to be 1 minus C I log of T0. Because it's just a geometry that this happens. Okay? The 2, okay, this bad event, the probability of this event, independent condition on everything that occurred before, Li minus 1, is bounded by this one. Because I said the probability I have a gap is that, and that's going to be this. Okay? With k equal to 4. Okay. The other thing is that I want to say that in this interval, I want to navigate from here to here, from somewhere here that I didn't say very well where, because it has to do with this power. I want to navigate easily from here to there. That means I don't want crosses here. So in some interval of some part of my interval, and I'm going to put that as assumption. So if I don't have any cross, then I just have a Poisson process that has to go from here to here. I mean, I can easily compute. So I put this, there exists a k in L I minus 1 plus 1 up to Li, such that dk are the death marks, intersection k cross T0 2 to the I minus T0 2 to the I to epsilon 4 that's bad. Here in my notes I changed epsilon 4 to gamma, so better I put gamma and put gamma there, no? Gamma, 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 okay? That's the gamma. So the probability that I have this guy now empty, I didn't write, 2, 0, 2 to the I. This is the interval, that this guy is now empty. This is the second event. That means that I have here in my this is my interval of no gap, but inside this interval I'm saying that there is some part here, here, T0 2 to the I up to T0. It has to be well located, no? Because it has to be, I am not drawing properly, but I know where it has to be. It has to be located close to this one, okay? Decay are the set of, maybe I should write RK, because are just the renewals, but they have a site also, because the renewals, I'm just saying the times. When I think of the renewal process, I just wrote decay. Let me write what it is. I don't know. I think my notation was that, no? J going from 1 up to n. Yeah, just because the renewal, when you think of a renewal process, is just time. So you're just thinking of these things without the other coordinate, which was the x. So I have the other coordinate here. Okay? So here is k. K. That's this one. Intersection k times this, then this is no empty. Okay, that means there is something bad there. And the third is very simple, that I can go from here to there by a Poisson process. So instead of writing in detail, but you could write like that. So there is a certain distance. So you split one by one, split in pieces of equal thing, and then you say there is a mark here, there is an arrow 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 here. Wow, it's a trivial way to get. Just a Poisson process travels this distance within this time. The distance is I log T0, and the time that you have at your disposal is T0 to the I to the gamma. So it's clearly that you are in good shape. Because the distance is just I times log of T0. And the time is like that, sub-exponential in I. And that is the T0, okay? So maybe instead of writing all these things which I draw there, I just say that Poisson process goes from one to the other. Right? Connect between this one, what I draw here. Okay, so you have in L I minus 1, that's 0. This interval I can connect, but I connect there. But I just use this piece, because this piece where I know that there are no dash marks. So it's just a Poisson process. There are no marks, okay? So I put that. Then you can prove, let me call BI these things, okay? BI is this, okay, let me be more precise here, maybe. Well, I say the sum of these probabilities of I is small. Less than 1, but I can make it very small because the sum of this guy is, well, it's 1 minus C to, no, because there is an event I. Okay, this one is, well, you know what it is. It's less or equal than the sum of 1 minus C to the I log of T0. So you can make this guy as small as you want. It decays exponentially. Okay? Then you compute this guy given that one, because that one, the probability that this happens finitely many times is 1. So you got this, assuming that that doesn't happen, and you control also because it's that's where we use the crucial thing. That's this one. Okay, using the proposition, you control this guy. It's small, using the main proposition. Because you know that the probability that you have a gap here is bounded by the t, which is t0 2 to the I, no, this one, 2 to the minus, that one. It's you can control.
Li is also dependent on the function of k.
K, no, this small k is changing. The big K is fixed as equal to 4. I'm using always 4. I'm going from 4, this I'm multiplying by 4, always 4.
This is a capital K.
Here?
Yeah, this is capital K.
No, it's small k. Small k. So the capital K is fixed at 4. This is always 4 here. So it's fixed as 4. And now you just have that the probability of this, if Li minus 1 is smaller than this number, because I'm assuming that I'm not on this, then I just use this proposition. I will get this E log of T0 times the probability, and that's going to be a very converging sequence also. Okay, so I get that one. And then the other one is also simple because it's just a Poisson process, has to reach a distance which is much shorter than the time. So the very trivial estimate of a Poisson process, the probability doesn't happen, decays very fast, exponential. So if I call BI the fact that one of these doesn't happen, no, then I have that the sum of the P of probability of BI is decays exponentially. BI is the bad event of I, that means this or this or this. You know. Bad, B, the bad. But it could be bom also. But bad, I'm talking in English. BI is that one of these bad things happen. So the probability of BI decays exponentially. So probability of BI, no, BI is I is less than constant. Well, no, let me write another constant, e to the minus c tilde ci. That c is not the same, so let me put, say, I don't know, c tilde and this without tilde. Okay? And if you make t0 large, c tilde you can make as large as you want, because it will be a function of t0 with log of t0. So you get that that you have the sum of the p of bi less than 1/2, or less than 1, just that, for t0 large. Just because making t0 large makes you make c large. C will involve log of t0, some c. And not exactly log of t0 because there are the other guys, but it's all these computations are very simple. So you see that this is going to be less than 1. That means that it remains this guy. It remains to survive here. No? Once it survives here, then it will survive forever. So, take T0. For any lambda positive, there is a positive probability of A0. So then it goes. So it's the argument is very simple once you have that proposition. So I say that proposition is not simple to get this. And this thing could be much simpler if you were in the domain of attraction of a stable and you'd just use the renewal theorem, which tells you about the usual notation of renewal. So this is expected number of renewals between t and t plus 1. And if you use that, the renewal theorem for non-integrable random variables. But this is known for alpha, at least for alpha larger than a half. You would be able to get in a much simpler way.
Where did you use
The assumption on mu, I use it crucial here, that I have this estimate. The probability that I have no gap, that I have no mark here decays fast like that. The probability that I have a mark here decays fast. That the intervals are very long. For integral random variables, this is not the case. So if you replace this guy by what you know here, that this is going to be C divided by L of t, t to the 1 minus alpha, where the expected number of renewals, and this is the, alpha is your alpha, L of t your slowly function.
Does this follow from the renewal theorem?
No, we are not in the domain of attraction. This doesn't follow from the renewal theorem. If we were in the domain of attraction of a stable, we could use the renewal theorem and get something more precise than that. That doesn't follow. So if you were in the domain of attraction of a stable, you would use this, where this is just expected number of renewals in this interval, and there is a theorem that tells you that. And then, this theorem is, it's not so old, but there is a theorem in the 70s and another one, at least for alpha larger than a half. But that would be a way to do. But we need much less, so we just need, but anyway, we need a power, positive power, so we need that. So that can be done like that. So I think I am, can I have 10 minutes to tell about the other? Yeah, I lost all the time. I spend all the time with this one. It's 3. Can I just tell a little bit about the other, because I think it's nice. So at least I tell about what is the idea. No? So about theorem 3. Theorem 2 I don't need. So the situation is the following. Why that assumption allows us to do things. I just tell why that, and I don't take your time too much. The following. So I said we made assumptions that D is 1 and that decreasing failure rate. Why decreasing failure rate first? Well, it allows us to get the following. Suppose you want to construct your renewal process. One renewal process, single renewal process here. 0, the first time, I want to construct this. And I want to make a construction that shows to me that I'm going to have some FKG type of property. Okay, so I do the following. You can construct the renewal process. You can always construct like that. If you have a density, H, so I'm assuming H is decreasing, but the construction you can always do, you have a renewal process, H is your hazard function, the failure rate, and it's here. And you can construct your process in the following. This I'm constructing a single process. So
this is H and this is the density of the...
This is H. So I define H here. So in my example is decreasing, so I made it a decreasing function. Okay, so I imagine that on the plane here,
H of t is f of t divided by mu t.
Yeah, exactly. So here I have a Poisson point process. This is a construction that it's always true. I imagine I have a Poisson point process with rate 1. Okay? So, and I want to construct my Poisson, my renewal process starting at t0. So if I want to start at 0, this is 0. If I want to start at t0, this is just t0, age of t minus t0. Just shift. Okay. So what I do? Well, I take my Poisson process, I look the first mark under the graph of age to the right of the point where I'm starting. I have, this is my age of t minus t0. Now t is very, yeah, so this is, I don't need to draw like that, but it's age of t minus t0. So imagine that you want to construct a process. Okay, you take the first mark, which is below the graph. So it's trivial, no? That the probability that you don't have up to s, let's say t0 is 0. No? Du is exactly what you want, the f, because it's f, small f divided by 1 minus f, it's logarithm e to the minus f. So it's a distribution with what you want. Okay, so you take this guy, and well, I mean, you take this guy, and now you want to construct another one in the pattern. So you just shift here, you shift, now you shift your process, and you start again. You put here and start looking, age of t and start looking again. Okay, so it's trivial that if you do that, you have something which is increasing in the Poisson process. If you add a mark to your Poisson process, you get something with more points, with more marks, because, well, I mean, if this is before nothing happened, when you are here, then instead of shifting from here to here, you have to shift from here to here. And maybe by doing that, you caught someone which you wouldn't catch otherwise because the guy was above, because age is decreasing. I mean, the construction is for every age, but increasing is if age is decreasing. Because age is decreasing, each time you push it more, you get more. Push it back, you get more people. So this tells me that I can take a Poisson point process and construct my renewal process as an increasing function of eta. Okay? That's all what this says.
Eta is
A Poisson point process. It's an increasing function. Okay, so
you couple two Poisson with different parameters, one below another.
so yeah, if I take two configurations, eta prime has more two realizations. With more, I will get more. It's an increasing function. So now this is true for any of these x, and you take this Poisson process independent. Okay, now, I mean, our process that exists a path is an increasing function of the Poisson process of the arrows and a decreasing function of the crosses. Okay? Because the more crosses you get, the less paths you get, the more arrows you get, the more paths you get. So it's, then I'm going to say that an event A, event in my this contact renewal process, is increasing if increases in the NXY, well, I just do one dimension, and decreases in the X, in the R's, because that's what it is. Okay. So this is my definition of increasing events. So, since for Poisson process, you do have the FKG property because you can approximate by Bernoulli's and the usual FKG of Harris. it follows that if I take A1, A2, and so on, AN increasing in this definition, I'm going to have my probability of A1 inter AN bigger or equal than the product of AIs. So in this sense, because it's an immediate consequence of the FKG property for Bernoulli. The usual way you have a FKG process for the contact process, because you can approximate by Bernoulli's, and you do that. So we have this property. Why this is helpful? This is helpful because of the following. Our proof is based on the following argument that we want to prove. We want to say that given that I have this alpha bigger than 1, I'm going to be able to find the beta positive. I'm going to look boxes which are of this. They are very small here compared to this. This is space, this is time. They are very long. Okay? This is 2 to the n beta, and this is 2 to the n, and n is very large. And beta is positive, but very small. Beta is going to be less than alpha minus 1. Okay? And I want to say the following. If I look at some number which I'm going to call Pn,
Alpha is exponent. What is alpha?
alpha was a moment which is bigger than 1, which is finite. So if I look at Pn, it's going to be the supremum, because I can condition on anything here below for the renewals, of the probabilities that I have a crossing, what I'm going to call a time crossing, or a space crossing of the box. What I don't want to spend time telling you what it means, but time crossing means that I have a pass from the low to the top inside the box. And a space crossing means that I have a crossing from left to right inside the box. And it's a pass in the thing. So copy Pn like that. This Pn. The main point is to show that Pn, there is a beta, there exists a beta positive, such that Pn goes to 0 as n goes to infinite. Pn is the supremum of the probabilities for any realization of the renewals here, that there exists a crossing, time crossing or a space crossing. This is in this box. So there is a multi-value scale. As you change scales, there is another scale. And the argument, the thing is to show, this one proves the theorem. I guess this is simple to believe why this proves the theorem. But before saying why this proves the theorem, because in order to say why, I would have to go to why this FKG is used. So suppose you want to control the time crossing that you can cross, the probability of crossing from down to top with with space probabilities, because it could be that the guy makes a pass very bad, but makes not so bad, not so horizontal, and still you need to arrive there. And why this is useful? Because, say, let us suppose I have boxes like that. They are all the same length, these guys. This is a fixed length, L, say, this T, so something fixed like that. And I'm looking at the following events, that there is a path that starts a vertical crossing from here to here. This is an event. Call it A0. Now I look at the events that there is a path from this one to this one. So the first is a little bit Okay, then I do like SUI. Okay, and you do this event. So these are A0, A1, A0 goes here, A1 goes here. So even go to the right and left go to, and odd goes to the left. And they cross each other because I'm forcing that arrives on the top and the other on the bottom. So if they crossing, if I have all these guys, then I have a vertical crossing from, say, from this epsilon, not from 0 because I started here, from epsilon to the top. Okay? So, and the probability of all this is bigger or equal than the probability of this intersection is bigger or equal than the product. So this gives me a relation between this probability and the other probabilities. And this relation is crucial to prove this, to control these probabilities, that we are able to prove that they go to 0. But maybe since my time is too short, instead of saying, why, if I prove this, I prove the theorem, maybe it's more, I think this is believable, but you have to think a little bit. It's more important that I tell why we can prove this. I think it's more important. So I spend a little bit to that. In order to prove that, it's a sort of recursion in the scales. So I need to say, what is Pn? Pn is this. I fix the scale. I mean, the beta is the one that I have to find. Is this one. Pn is the supreme of the probabilities that there exists a time crossing or a space crossing of these boxes. The boxes are like that. They get like that. And the reason is, well, I mean, you take a scale n. I need to find, I don't know, I said already what is going to be the beta that we need, but need to say. Okay, so I want to make a recursion formula in the PNs that will show me that they go to 0. And this is done, I mean, there are some lemmas which I'm not, technical things which I'm not going to say, but I'm going to do the following. So I have my box here, and you think that's very long, and like that. And I want to study about Pn in terms of smaller scales, Pn minus k. So I split this, so I have all these guys. No, this is, instead of being 2 to the n, this is 2 to the n minus k. Okay? So my drawing is pretty bad. So you have all these guys, 2 to the k guys, like that. Okay? Suppose I do the argument only for the time crossing, because the space crossing is easier because they are completely independent, and the time they are not. So let me think only about the time. I want to relate Pn to the Pn minus k somehow, because I want to get a recursion. And then, well, I mean, since I say that there is a time crossing, you know, so I fix some box here. There is a crossing, but this crossing doesn't need to be nice as I did. It could be horrible. And nothing to do with a box which is n minus k beta and 2 to the n. Could be much larger. So I need to deal with various cases of the estimates. I have a box and I have to cross this box in the vertical crossing using all these things. And that's where you see that this comes in, because I related one crossing which is not exactly horizontal with a vertical crossing. Okay, but where is it important? Once when you get this, to relate the two things, you know, you have to look several cases that can happen. But one thing is important. Let me do the following. I want to say that to estimate the probability Pn in terms of Pn minus k or something like that. I do the following. First, in order, you know, these things have some dependence because the processes are not independent. So I do the following. I split, exactly I did the bad thing, because this is one that I wanted to look and I erased. Okay, so this is something, and here I have something bad, which could be bad. Anyway, I split, I take two of the, I mean each two of them. In the other ones, this one which I marked, I am assuming that there is a cross mark everywhere in all sides. And I am assuming that if I look at the first time Tn, that I have one of these guys without any, missing one of these marks, that this probability is small. This is simple to compute because your random variable has a tail which decays t to the minus alpha, because it has moment finite. So using that, you can see that the probability that Tn is less than 2 to decay, that, which means that I am not in a situation that for all these guys I find one renewal. Because what happens when I find one renewal, I forget what comes before, because it's independent. That's why I want that. Okay, so this probability you control is small, decays because of the tail. I mean, you fix the k you are going to take, fixed. Tn is this. The first time I'm doing this game here, I'm saying, do I have, could be I do in the first, maybe it's what we do, but it doesn't matter. Do I have a cross everywhere in all sides within this strip? That's the second. Do I have one here? Yeah, across my renewal, a D. Because when I have a cross, then I forget that. A renewal point across, inside this. Okay, do I have, Tn is the first time that this fails. So, and they say less than 2 to decay, that fails before arriving to the top, because I have 2 to decay guys. And then we can see that taking beta less than that, and k fixed large, k we're going to fix depending on beta, but not depending on n. This is going to be small, less than 2 to the minus n some epsilon 0 there. Yeah, okay. And now you have the other guys that you have a vertical, you know that you have a vertical thing. So if this path were like that, all of them just having a path which would fit the scale, because here is, no, they don't need to be, when you look inside this, I fix one of these things. So this is 2 to the n beta, and this is 2 to the n minus k. So this is it's not compatible. So inside here, I have a crossing that goes from here to here, but this is not a crossing of p n minus k, because this is much bigger. So you need to prove that, to compare this probability with the probability of p n minus k. Okay? And using this kind of things, you compare, but you get a power, because you see that there was a power coming. And making computations and treating various cases, I mean, the paper has some technical things to be done. You can prove that if it's not the case, you get a bound which is p to the n minus k, maximum p n minus k minus 1 to some power 1 over 10 for each of these guys. So, but since you have a product here, because there are many of them, so once 2 to decay beats the 1 over 10, like 2 to decay is 20, bigger than 20, you get a squared. So you get something that tells you that your Pn is controlled by Pn minus k, maximum Pn minus k minus 1 squared. I think it's easy to believe that if you have a recursion like that, it has to go to 0. Because if you think of a function But there is something to be done because you need to play with the iteration, but I think it's believable that once you get something, p to the n, you control in terms of some smaller scale with a power 2. So you get that Pn goes to 0. And in order to say why Pn goes to 0 allows you to prove the theorem, you think of the following. Well, this is 0, this is time 2 to the n. You get that, I mean, I didn't give all the details because here, in order to come, I need, what I need, yeah, I cheated a bit because you say it's easy to see once you get that in the beginning it's small. And the beginning is small, you have the first scale, you need to make lambda small in order to get. Yeah, you need to make lambda small in order to get started your recursion. Okay, so now I want just to say that why, assuming I have proven that for lambda, because I didn't say the lambda is, I'm not writing, that is for lambda small. Well, I have a vertical crossing or a horizontal crossing. So if my crossing goes there, that's okay, because the probability of Tn tau survives up to this time. But it could be doesn't go there. No, it could be that exits this box from this side, and it could be like it does many things and then exits this box. So there are three situations. Or I exit from the top, because Pn I must exit this, or I exit from this side, or I exit from the other side. If I exit from the top, it's trivial because the process is surviving up to here. If I exit here, so I need to be careful and think, well, I mean, let's see, there is a path going from somewhere here, because since there is a time that last time it touched it here or whatever, and it goes there. So I have a spatial crossing from here to there. And I need to split into various cases and make a computation using this again and see that this probability I control in terms of Pn. Just that it's going to change the scale by a half, because this was 2 to the n beta, and it's going to be 2 to the n beta divided by 2. So instead of beta, is beta minus 1 over beta, something like that. Or, yeah, and then there are various cases. You need to, there is a lot of, these computations are all sort of, they are involved in some sense that you need to look various cases, but they are not too complicated they are not difficult to follow.
It's a very long sequence
But
of a very nice.
yeah, the main thing is that you are able to find a situation where you can explore RSW type of things, and that's more or less the idea. Sorry that I made something too long and maybe probably very confusing.
The paper is available at the archive.
Yeah, the first one is already accepted and it's online on SPA. The second one is still under review. I don't say the journal because then it might be rejected, so it's bad if you say the journal. But the other one is under review, but both are on archive. Yeah, maybe the first one we didn't put the corrected version on archive, but the corrections were pretty minor, no, Domingos? The corrections in the first were pretty minor. The second we changed more, so I should update the archive because the second required much. We had to improve the presentation so that the reader can follow. No, we don't have three, just two. 3 theorems, but a paper can contain more than a theorem. No, that's okay.
Thank you, Eulalia.
Thank you.
No questions? Okay, I have a very So it's my function to ask questions. So you don't use duality here because you don't have duality.
No, duality, no.
Yes, so you don't have.
No,
Okay.
no, don't.
So it's very nice because
No,
succeed
yeah,
doing
there's
this.
No duality, yeah, we just, the only property that we use is this
Is attractiveness.
This FKG type.
So since you don't use duality, so one of the nice things about the contact process is that it's self-dual. But this is not self-dual, it's not dual.
Yeah, yeah.
So in principle, this is more general. Your result use less than the contact process. This
No, sure, we use, that's why we had to work, quite a lot. The other thing which I didn't say, maybe I should have mentioned, because it's natural. If you were thinking of infection model, it would be more natural not to look, maybe thinking of infection. Thinking of percolation, this is the model. But think of infection, maybe you want to consider the following thing. The guy is here, now suppose the guy started infected, and here it will be cured, but here it transmitted the infection to this guy, and the time for this guy starts counting here. So the T is the time when it stays infected. So this is the usual SIS model. Susceptible, infection, susceptible. The time of the infection, because the person is infected, is got a cold, and takes some time to recover. No? Mm-hmm. So the time you start counting here. So this is, say, T1. No? And then this guy got cured here. Okay. If it was, then you have to see what you do. If the guy got another virus here, then maybe you disregard, maybe not, I don't know. But if you do this type, this is a different thing. So one thing is, it is easy, is that if it will not survive for lambda very small. The second theorem, that's easy here. With the same idea somehow. But the other one, I don't know. That's a different model.
The epidemic will not survive.
It's a different model, yeah. It's a different model, but we thought a little bit. The other thing is, the other question regards strong survival, because we just said that survives, we just use going direction, so it goes away. But if you are in the, this is something, if you are in the domain of attraction of a stable alpha small, I think there is a student of Remy Sanchez with Renato and Remy, maybe, they are proving that you survive on a strip, on an interval. So there will be, but I don't know. Our theorem 1 is under much stronger and much weaker conditions, so I don't know if that is the case. We didn't check. And the other thing is, the other question is, this process has the potential to have a different behavior near critical. So I don't know if it at criticality it survives or not, because the contact process doesn't, but here we don't know. This is open. But we didn't think about that for the moment.
Okay, so let's think about it.
Thank you.